طيب بسم الله الرحمن الرحيم. So today inshallah we're going to start a new chapter about multimedia networks in wireless metropolitan area networks. So for metropolitan area networks, as the name suggests, we talk about wireless networks that cover long range, relatively long range. So for wireless LANs, we talked about relatively short range, because we have shorter range when we talk about personal area networks. We talk about very, very short range communication. So wireless LANs, they talk about short range communication in a geographic, in a small geographical area. Metropolitan area networks talks about an internet access replacement. So we talk about long-range communication where we can actually use metropolitan area networks to cover a whole country. Okay, so in which case these wireless technologies can replace completely the internet access technologies, like for example DSL. We have DSL at home to connect to the internet. Of course, now we have fiber optics. But these types of wireless technologies can completely replace the internet access technologies like DSL. In which case, you don't need to have any routers at home. You don't need to have you don't need to connect to any special network at home to be able to access the internet. You can use these types of networks directly to connect to the internet. We have many examples of these types of technologies that we have nowadays. We started with GSM. GSM is the most dominant wireless technologies for long-range communication. And we have, later on, we started to use 2.5G and 3G and 4G, and right now we're talking about 5G types of networks. So, of course, our purpose in this course is again to talk about these standards from the dimension of providing multimedia communication. So what we need to do again is to try to understand the special components and mechanisms in these standards that are related to how to facilitate the transmission of multimedia content, in which case we need to again look for how we can support quality of service, how we can provide guaranteed quality of service, and so on. As I said, there are multiple wireless technologies in this category. One of them is what we will talk about, which is 802.16.1. So in these types of standards, we can talk about providing backbone types of networks where we can connect multiple wireless LANs through a backbone network. In which case we have here, like here for example, we have in this house, we have a wireless LAN, here we have a wireless LAN, and here we have a wireless LAN. And in order to connect these wireless LANs using infrastructure, which is what we have called extended service set or ESS, we can use, instead of using the infrastructure, we can use wireless backbone as metropolitan area networks. In which case, we have like a small tower in each of these buildings, and these towers, they connect to each other in another level of wireless network. And in these cases, these small towers can have the communications in two ways. Either these towers need to communicate point to point between each other, in which case you need to have like a line of sight. So they use some type of directional antenna and they connect to each other in a line of sight fashion. Okay? There are some advantages and disadvantages to these types of communication. Or we can use similar technologies like in cellular technology where line of sight is not required. Okay? So in which case our phones, for example, do not have to have line of sight to the base station, right? So we still use cellular networks. So in that case, there is no line of sight. But in that case, there are some special characteristics that we need to have both on the device level as well as on the base station level to be able to communicate in a non-line of sight fashion. So that's what we need to talk about, and we need to talk about how we can provide quality of service in each type of communication. So basically, in this chapter, what we going to be covering is 802.16 family, all right? So in the previous chapter, we covered 802.11 family, right? Here, we cover 802.16 family. And again, similar to 802.11, here we have different variations also of this standard family, and there are some characteristics that distinguish each one of these variations of standards. So first, we're going to talk about an introduction, and in the introduction, we will talk about the high-level differences between these different variations, and then, similar to what we have done in the previous chapter, we will talk about physical layer and what are the technologies and the characteristics in the physical layer that will allow us to have any kind of quality of service, whether guaranteed quality of service, is there like some type of collision, does it support collision, does it not support collision, and so on and so forth. This is in the MAC layer level. And at the end, we are going to talk about how we can support quality of service. So using all these characteristics in the physical layer and then the MAC layer. So now we need to talk about the mechanisms that we can use to provide quality of service in both its aspects. Again, providing service differentiation. So how can we differentiate between the different stations, and also if we can provide some guaranteed quality of service, in which case we will have a predictable type performance. So first, an introduction. The goal here is to provide, the goal of these standard families is to provide high-speed internet access. So in that case, we can provide internet access to the subscriber stations or to the users directly. So the users do not have to connect through their home network, through ADSL, to be able to connect to the internet. They can directly connect to these towers, okay, and they can get internet access through these towers. And in that case, without wires, of course, so we don't have to have wires at all, or we don't have to have any infrastructure. And we have base stations, and base stations here are relatively large scale towers that need to be set up in different locations, different strategic locations, to be able to cover the whole country. And depending on the locations of these towers, so you can have high coverage or low coverage, and in some cases no coverage in certain positions in certain areas. For example, I'm sure you have been in some buildings where, like, when you go and use the elevator, sometimes you see your phone with no coverage, or you see the signal very weak, or maybe no signal. So this is the type of coverage that we're talking about. So maybe in certain locations, in certain indoor areas, you may have some coverage, low coverage, high coverage, no coverage. So that depends heavily on the locations of these towers and where you are in relation to the location of these towers. Okay. The one distinguishing factor in any of these types of networks is that the access control prevents collision, and this is the comment that I said at the end of last lecture, is that Wi-Fi is the only standard families that adopted or advocated the use of collision-based access techniques, right? And the main purpose of this is by leveraging these collision-based techniques, we can have the maximum throughput. And as we will see here, for these techniques, although collision is eliminated completely, but they require huge amount of intelligence in order to be able to manage the resources of the network. Whereas for Wi-Fi, it's highly distributed, and you don't even have to have a hybrid coordinator or a centralized node to coordinate when the nodes will access the medium. Okay? But here, the towers need to be engaged at every single point to manage how the resources are divided between the different subscriber stations, and that requires really high level of complexity. So the towers are very, very, very complex devices that need to handle how the medium will be accessed.
Are these towers like, say, Origo or Vodafone?
Yeah. Yes, that's exactly what I'm talking about. And these towers, as I said, need to be deployed and set up in very strategic locations, sometimes on top of the buildings and sometimes in separate areas. Of course, there are so many issues with this, whether they use renewable energy or they use what type of energy that they use. But they are heavy equipment, they are heavy towers, and they require a huge amount of energy. So you cannot just carry one base station with you and move it somewhere else. It's not easy. Although nowadays, as part of 5G, they are talking about a stripped-down version of these towers now, which is what they call Pico Cells or femto cells or something like this. So I'm imagining in 5 years or a few years down the road, we will have a stripped-down version of these base stations in our houses. Whereas this will actually increase the coverage and will increase the capacity of the network and so on and so forth. But these are new technologies that will be realized as part of 5G. Okay. Type. Originally, these networks were realized to support voice communication. Okay? And in fact, this is the main reason that they have eliminated collision. Because at the beginning, when they designed these networks with the perception of providing voice communication, okay, there's no way you can have collision in these types of, because as we said, for voice and video, in order to be able to have predictable performance, you need to have circuit switching type networks, right? So that was the main reason that from the beginning, these types of networks, they took the route of not accommodating or providing collision-based techniques, okay? So from the beginning, they took the route of some like Cdma or Fdma type technologies where they can divide the resources of the channel and give each user a specific share so that he or she can provide voice communication with predictable quality. Because as we have mentioned in early chapters, we said that if you want to have ideal type of quality of service for voice and video, you need to have a circuit switching type connection where you establish a circuit, and then once you establish that virtual circuit, you can have communication, in which case you will have the packets ordered and you can have some predictable performance in terms of delay and throughput and so on and so forth. Because this was the original objective of these types of networks. That's what they have advocated, is to use a collision-free environment. Okay, but later on, they started to look into some data services, providing data services on top of these networks. So they kind of evolved from a purely circuit switch type networks into a mixed type networks where you provide circuit switching as well as packet switching. So having these two types of technologies provided on the same network, on one hand, requires huge amount of sophistication in terms of how you design your network, but on the other hand, has opened the door for diverse set of applications where you can provide voice, you can provide video services, you can provide data services, and so on and so forth. So the original objective was to provide voice communication. However, this has evolved into also providing some data services and later on some quality of service requirements. So you have Wi-Fi on one hand, where it was originally designed for data, and cellular networks or metropolitan area networks where it was originally designed for voice. That's why for Wi-Fi, for data services, collision-based techniques provide higher throughput actually. So ideally will provide higher aggregate throughput, okay? And for metropolitan area, because you have voice services, they opted to have a collision-free environment. But nowadays, we are talking about the concept of network conversions, where on Wi-Fi, they started to increase the usage of HCF and PCF, where you have pulling mechanisms and have collision-free. And this will be particularly useful for the case of providing quality of service for multimedia applications, right? So as the 802.11 standards have evolved, they started to promote the usage of PCF and HTF and these kind of things. On the other side, as well, for metropolitan area networks, they originally advocated the use of Tdma or collision-free type access control for the medium. And later on, they started to have smart techniques where you can divide these resources of the channel amongst different users to provide quality of service and differentiated services and so on and so forth. They did not get into collision-based, so from the beginning they started collision-free, okay? And they did not try to engage into collision-based types of techniques to control the access to the medium, okay? But as we will see later, they have really spent huge amount of investment on how we can make the access control to the channel as smart as possible, and that's what we need to discuss. But the idea is that for both types of standard families, they try to increase the usability and the diversity of the applications that can be provided on top of these types of networks. For cellular networks, they started to have data services. For Wi-Fi, we started to have multimedia services, like voice communication, video communication, and so on, okay? So these are some variations of these standards. So you have 802.16.1. This is the first baseline standards. And as you can see, this type of standards, 802.16.1, it uses 10 gigahertz to 66 gigahertz, okay? This is a very high frequency, okay? It turns out for wireless signals or for any type of electromagnetic signal, as the frequency goes high, okay, as we have mentioned before, the signal tends to lose its power much, much faster, okay? And in this high frequency, the signal, in fact, suffers from like some dispersion and some, so you can easily, for any kind of obstacle, it actually, the obstacle absorbs completely the wireless signal. In which case, for this high level frequency, you can block the entire communication easily by having an obstacle in the middle. Because this obstacle is going to absorb the entire energy of the wireless signal, okay? And that's why in this high frequency, the only way you can have communication is through a line of sight. And by line of sight here, we mean that you have to direct the wireless signal towards a specific direction, and the device or the base station that tries to communicate with this base station has to be on the same direction where the wireless signal goes. Otherwise, if you have any deviation from that direction, you will not have any communication. Similar to like the remote control that we use at home for TV. Okay? So you have to direct the remote control towards the TV, otherwise you cannot control the TV. Why? Because these remote controls, in many cases, they use infrared, which also uses very, very high frequency signal. And in this high frequency signal, the only way you can have communication is through line of sight. However, in this line of sight, you can have very accurate wireless communication, in which case there's no interference, right? Because all the devices that we talked about before, they work in low frequency range. So in this type of frequency, you can have no interference whatsoever. And in that case, you can have very high bit rate. This is not the highest, by the way, because as part of 5G, they are talking about maybe 1 gigabit per second. So this is actually not the highest bit rate that you can have. But this is when the standard was first released. So this was considered to be very high data rate at that time. Okay, so 134 megabits per second. So you can have this high data rate, okay, if you use very high frequency, but this will require that you have to work line of sight. Okay. So what is this good for? Well, this is good for point-to-point communication. If you have these towers, so these towers can have like an ad hoc network between them, where each tower can communicate with the other tower as point-to-point. So in that case, you can have very high data rate using line of sight, so you can use this wireless network as a backbone network. So all the subscribers, they send their traffic to this backbone network, and this backbone network will carry the aggregate traffic from thousands of subscribers, okay, through these towers. So the towers themselves, they communicate using 802.16.1, using line of sight, very high frequency, and very high data rates, right? So that's one variation. However, it didn't stop at this point because, again, well, this does not really facilitate, the communication of this type of cell phones, for example, because we cannot afford the fact that these cell phones have to use line of sight with the base station. That's not what we hope for. So 802.2 is another extension to 802.1, which tried to address the coexistence of multiple 802.16.1. So it tries to address the coexistence of these networks together, in which case you have to use space diversity and, in some cases, frequency diversity to be able to have multiple of these wireless metropolitan area networks to exist in the same geographical location. Okay, so this is like just an extension of this. The important thing is 802.16a. So this one supports actually the communication between our cell phones and these towers, and that's very important because we cannot have line of sight between the subscriber stations and these towers. Okay, so we need to have non-line of sight, and also to support very high frequency signals for these devices. This means that the range of communication will drop, right? Because as we said, in this high frequency, the wireless signal tends to lose its energy much faster. And also this will not be good to communicate in indoor areas, right? Because all these obstacles will absorb the wireless signal. So that's why for 802.16a, it works in low frequency range. So between 2.4 gigahertz, similar to Wi-Fi, all the way to 11 gigahertz in very special cases, right? But not as high as 66 gigahertz, because in this high frequency, you cannot have indoor communication at all. And all these obstacles will just absorb the wireless signal. Okay? And in that case, the important thing is that it's non-line of sight. So you can have communication wherever you are. Okay? And of course, the rest of these are just, an extension and tries to enhance this by using different frequency and so on and so forth. So that does not concern us very much. So here in this chapter, we'll focus mainly on 802.16.1 mainly. So we'll focus on the line of sight communication in very high frequency. And in that case, we will focus on the structure of, or the architecture of the physical layer, the MAC layer, how they are, what technologies are used in each of these layers, and how does that facilitate the quality of service support in terms of service differentiation and guaranteed quality of service. So one thing we notice here is that 802.16.1 is built with lessons learned from Wi-Fi, right? So Wi-Fi, it started with no quality of service support, and then it evolved into 802.11e, which then incorporated some quality of service support into 802.11, right? But here they started from the beginning with the quality of service in mind, okay? And that reflected on the architecture of the layers, okay? So we see some significant differences in the layering stack for 802.16.1 compared to Wi-Fi. So there are some differences. Still we see Wi-Fi, still we see like physical layer and data link layer, so that's not going to change. But the structure of the sub-layers and what is the functionality of each layer is different. So here, for example, we started to see a privacy sub-layer. So even security is built into the standard from day one. So they started to have security because, again, as time goes by, we are realizing the importance of security. So from day one, 802.16.1 is built with security in mind. Also here, we see service-specific conversion sublayer. So this sublayer provides specific services for certain category of applications. Like here, we have service-specific conversions sublayer, for example, for voice communication or for video communication or for different types of applications. So this sublayer customizes the traffic that is coming from the higher layers to provide a specific service. So for example, for voice, we need to create specific streams with different quality of service requirements that to be actually transmitted over the physical layer. So we have conversion sublayer for voice versus video versus data and so on. So we have, this is called service-specific conversions sublayer. Okay, we didn't have that in Wi-Fi, right? So that's why I said that from day one, we built this layer architecture with security and quality of service in mind. So that's why we have these two sublayers which did not exist before. Okay. Other than that, this MAC common part sublayer, it controls the access to the medium, but in a totally different way. So here we don't have PCF and DCF and these kind of things. So as we said before, we're working in a completely collision-free environment. So we know that we can divide the resources of the channel. We know that we can divide this in time. We know that we can divide this in frequency. So even polling is not very much used here, although the base stations are allowed to, in some cases, pull certain subscriber stations to provide some predictable quality of service. However, other than that, we use Cdma and Fdma. So in Cdma, we basically divide the channel into time and give each subscriber station a specific time slot. Okay? And Fdma is to divide the frequency into specific frequency range. And we give each subscriber station a different frequency. So in both cases, if we divide the channel into time or frequency, we know that we eliminate collision. So if we organize this carefully, we will have no collision, right? So now it becomes the the functionality of this layer to know how we can divide the time, or how we can divide the frequency, or in some cases, mix between the two. So divide the frequency and on top of that, divide the time. So what time and frequency we give to each node? That's the question now. And this sublayer controls that. And again, similar to Wi-Fi, we have a complete, a separate plane called management plane. Okay, similar to Wi-Fi. So Wi-Fi had that. So we have a management plane. And this management plane is separate from the data and control plane. So this is the data and control plane. And this is the management plane. In the management plane, we can configure each sublayer. And by configuring each sublayer, we mean that we can set the parameters of these sublayers. So each sublayer uses certain parameters. Like مثلا, for example, for Wi-Fi, we have a collision window or contention window, we have a persistence factor, we have DIFS, SIFS, something like that. So we can at some point control these parameters, okay, through this management plane. So this is the plane where we can configure each of these sublayers. Okay. So in terms of physical layer, the first thing we notice here is that there are no subchannels. Remember, for Wi-Fi we had 3 non-overlapping channels, or 11 overlapping channels, or in some cases, I don't know, like 128 subchannels. So we divide the whole spectrum into small subchannels, and then to address the co-location, okay, we allow each node or each access point to use a specific channel, right? And then we may use frequency hopping to hop between these channels to facilitate the interference. Here we don't do that. We use the whole spectrum as one unit. Okay? So this is the first thing. We don't have any subchannels. We have the whole spectrum as one unit. So the base stations, and again here we're talking about very large scale base stations, and they communicate point to point. We use the entire spectrum as one unit. We don't have channels. And the reason for this is that we try to eliminate interference by direction or by having the line of sight. So we're expecting the fact that we do not have co-location issues, in which case we need to have different channels and use, for different communication, use different frequency and so on. We don't need to have that because we are separating the interference through direction, through point-to-point direction. So you have, again, برضو عشان يعني, just so people can imagine what I'm talking about. We have a node with, this is an antenna of communication, okay? And you have a node here with another type of antenna. So this is what we call a directional antenna. So this directional antenna sends the wireless signal in that direction. Okay? So if you have this wireless antenna that sends the wireless signal in that direction, so although wireless, you send a wireless signal in the space, but in that particular scenario, these two communications will not affect each other. Why? Because these directional antennas, they tend to focus the energy of the wireless signal in certain direction, right? So in that case, even if they are using the same frequency and send at the same time, it's as if you are sending on two different lines. Although we're talking about wireless signal. But because of using directionality as a way to control interference, on one hand, we lost the benefit of wireless being a broadcast domain, right? But on the other side, we can control the interference this way by focusing all the energy of the wireless signal in certain direction. So in order to have communication with this node, then you need to have another antenna here. If this antenna is here or this way or something, you will not have communication. So this is what line of sight means, right? Because of this line of sight, we can have no interference between this communication. In which case, we don't have bad to have any co-location issues and different frequency range and so on and so forth. We don't need this. So that's why in physical layer, the first thing they have discussed in the standard is by having single carrier. Okay? So in Wi-Fi, we use like 20 megahertz, and then we divided this into subchannel. Here, we're actually using around 20 to 28 megahertz as one carrier, one signal. Okay? And of course, we allow the use of directional antennas, right? Which is what we have explained here. And we use for duplexing, which means that for any two communication to happen at the same time, like you are sending in both directions, you're sending and receiving at the same time, you can either use FDD or TDD. So this is different from Cdma and Fdma. Okay? So this is to facilitate the duplexing, or sending and receiving at the same time or at different time. Basically, TDD talks about sending in one direction at one point and then receiving at another point. So you basically send and receive on two different time slots. Whereas FDD talks about the fact that you send and receive at the same time but on two different frequencies. In which case you need to have two transceivers, one configured at one frequency and the other is configured on a totally different frequency. In that case, you can have a bidirectional communication at the same time, but on two different frequencies.
Doctor, regarding the way, like the communication at which you would either send or receive, would that show the effect to the end user? For example, you would be able to see through the logs when you're using a device that uses the antenna and stuff like this. Would you be able to see that, at this point your connection is down because you're receiving information?
So basically, when we talk about the format of the frame, you see that the frame itself is formatted in a special way, and it's divided. This is for this direction, and this is for that direction. So they are separate in time. Or if they are parallel like this, but sent on two different frequencies, so in that case, you can have bidirectional communication at the same time. But in that case, you need to have, in the physical layer, you need to have two transceivers, one for sending and one for receiving. Two separate transceivers. Okay? Each one is adjusted at totally different frequency. Okay? So we'll have to